Today's video is on accelerators and detectors. Likely to be quite a long one, but accelerators and detectors work on the same principle, so it didn't really make any sense to break it up into two separate videos. So bear with me. The first thing we're going to do is talk about electron volts. Now this should be relatively familiar to you from quantum physics work last year, but it bears going through just in case. The electron volt is a unit of energy, and it is used for very small energies, typically those that particles get when they're accelerated through an electric field. It comes from the equation from electricity, V is equal to W over Q. So 1 volt is 1 joule per coulomb. If we rearrange that, we get W is equal to Q times V. Now when we're talking about a single electronic charge, whether that be positive or negative, that Q becomes a small q. Now remember, sometimes you'll see this written as an E. Even though our specification gives it as a Q, it has come up in questions before as an E, so it could be given as a small e. So the energy gained by one electronic charge is Q times V, and of course this is the idea that Q has the electronic charge E and the volt is there. So the energy gained by one electronic charge when it's accelerated through 1 volt is 1 electron volt. We know that electronic charge is 1.6 times 10 to the minus 19 coulombs, and therefore this is the conversion factor for electron volts to energy, because 1 joule is equal to 1.6 times 10 to the minus 19 coulombs times 1 volt. So therefore 1 electron volt is equal to 1.6 times 10 to the minus 19 joules. 1 electron volt is a very small unit of energy, and generally when we're talking about accelerators and detectors, we're talking about particles that have been accelerated to greater energies than that. So for example, 1 mega electron volt is a classic. 1 mega electron volt is obviously 1 times 10 to the 6 electron volts, which means it's 1.6 times 10 to the minus 13 joules. For even faster particles, we talk about giga electron volts, and that of course is 1 times 10 to the 9 electron volts, which would be 1.6 times 10 to the minus 10 joules. We're just taking that 9 away from the original minus 19. Now obviously the electron volt is a unit of energy, but we also know that E is equal to delta mc squared, Einstein's equation, which we will be coming back to repeatedly over the next couple of videos. And physicists at this level stop separating the idea of mass and energy because there's a multiplication factor between the two. C squared is 9 times 10 to the 16, which means that essentially mass and energy are the same thing. They're just multiplied up. Mass is multiplied up by this factor to get energy, and energy is divided by that factor to get mass. And so we stop separating the two, and we stop thinking about the two as different things, and it becomes the idea of mass energy. And this is really important because, of course, we've been talking about conservation of energy for years and years, and conservation of mass is a principle in chemistry. But here we talk about the conservation of mass energy. Instead of just counting up how much energy something has or how much mass it has, you count them as a total. You look at how much mass plus how much energy it has. Now to do that, you kind of need to be using the same unit. And we'll come back to units of mass in terms of energy later on, but here we've got units of energy that can be used in terms of mass. So often you find physicists, when you read papers at this level, they will talk about electron volts as if they're talking about mass. Strictly they're not, and again we'll come back to that later, but electron volts, kilograms, mega electron volts, giga electron volts, these things start to become interchangeable in the vocabulary, and that is something that you need to get used to. Okay, so let's start looking at accelerators. First accelerator we're looking at is the LINAC, and it specifically mentions in our specification that you need to be able to describe both the LINAC and the cyclotron. Here's the LINAC. It is used to accelerate electrons up to about 50 giga electron volts. And so if you look at it, the ion source here is where, and let's just talk about electrons. You could just as easily do this with protons and accelerate those, but we'll talk about electrons. This is the ion source and the electrons are released from here. You have this oscillating supply, and what that does is it makes each section of tube oppositely charged. So as your ion source comes out here, what will happen first of all, and you can see that between the two pictures we get a change in the charge on each tube. As the ion source, if it's negative, comes out, that tube will be positive and the ion will accelerate towards that tube. As it's inside the tube, it is drifting. It has a drift velocity, and remember we have an equation for that back in electricity, and no force is exerted on the ion in the tube. When it reaches the other end of the tube, the polarity of the supply switches. And so that one was positive to start. This one will become positive as the electron comes out of tube 1 and is accelerated towards tube 2. And that just repeatedly happens over and over again. It drifts inside the tube, and as it emerges from the other side of the tube, the next tube along becomes oppositely charged so that it's attracted across that gap and accelerated. The tubes have to be longer as the electron proceeds down along the line arc, and that's because, of course, it's being accelerated between each tube, which means that it's going to be going faster, drifting faster inside each tube, but the frequency of the supply is fixed. So the time period at which the supply switches is fixed. So the tubes have to be longer because the electron has to spend the same amount of time in each tube before it comes out the other end. Now, this particular accelerator only uses electric fields. It does not use magnetic fields. In fact, it is shielded all the way on the outside from magnetic fields. You don't want the electron changing direction inside these tubes. It's a straight line. We just want it to go from one end to the other, and its speed to increase as we go along. So when we talk about being accelerated by an electric field here, we're talking about changes in speed only, no changes in direction. As you can imagine, there are limitations to a line arc because its length is going to determine how much acceleration you can get on these electrons, and therefore how much kinetic energy they can get. And when we talk about 50 gigaelectronvolts, we're talking about the kinetic energy that the electron has. So the more kinetic energy you want that electron to have, the longer the tube is going to be. And this is what limits the size of these line arcs. So this 50 gigaelectronvolts is the accelerator at Stanford, and that's pretty much about as long as they get. Electron line arcs are typically used in hospitals. They accelerate the electrons, and the electrons then hit a tungsten target, and that causes the tungsten to emit X-rays. Before we look at our second accelerator, we need to think about our equation R is equal to mv over bq. I've derived this equation in a previous video, but I think it bears repeating because we're going to be using it a lot. So where does this come from? Well, when you have a charged particle inside a magnetic field, it experiences a force. We know this, and I will put a link to my previous video if you want to have a look at charged particles inside magnetic fields. The force on a charged particle inside a magnetic field is BQV. That force is a centripetal force when the particle is moving perpendicular to the field. And so it becomes BQV is equal to mv squared over r. If we cross multiply this, BQVR is equal to mv squared. Obviously we're going to get cancelling of our v on the left with one of our v's on the right. And that gives us r is equal to mv over bq. And you do sometimes see this written as p over bq, which I think is what is given to us in the specification because, of course, mv is the momentum of the particle. But actually I think it's more helpful to leave it as mv over bq because we're going to be using the idea of the mass and velocity of the particle and how that affects the radius at which a particle moves. There are other derivations that we can do with this that I will come back to later on, but that is the principle. The radius of the circle in which a particle moves depends on these factors: its mass, its velocity, the strength of the magnetic field, and its charge. Here is our cyclotron, the second of our particle accelerators that we need to be able to describe. This one has come up as a 6-mark question on a couple of occasions. The line arc has not, because this one uses both electric and magnetic fields, which makes it a favorite of examiners because you have to be able to use all the principles. Okay, so let's have a look. Our ion source here is in the middle. So your ion, and again, let's just call it an electron, is released in the middle there. You have got an electric field between the two Ds, D1 and D2. And again, it's an alternating electric field, so it's going to change direction. So let's suppose at the start it's positive and negative. And of course that is going to accelerate our electron to the left into D1. The magnetic field runs through the Ds, so you can see on the picture on the left-hand side the way that the magnetic field is. So as the particle enters this D, it is curved because of the magnetic field. And remember, R is equal to mv over bq. Now, obviously mv and q here are constants, so our R is proportional to the velocity of the particle. So you can see in the first round here, we've got a fairly small radius because our particle is not moving very fast. But when it gets over to the other side, this is when the frequency of the supply switches. And so the other side becomes positive, that is D2, and D1 becomes negative, and the particle is again accelerated across this gap, so its speed increases. So electric fields are used to change the speed, the magnetic field is used to curve the path of the particle. Now, because it's moving faster, in D2, we're going to have a larger radius of curvature, and around it comes until it gets to the other side here, and the same thing happens, we get a switch. Now, of course, it's going to spend the same amount of time in each D. There's no reason why it would not. The curvature is larger only because the particle is moving faster. It gets accelerated again into the other D, round it goes in a larger radius, and that keeps repeating until, depending on the size of your cyclotron, it emerges out here as a beam of electrons or protons or whatever it is that you're accelerating here. The plus points of a cyclotron over a LINAC, of course, is that it's more compact. It doesn't need to stretch for kilometers. You can build these things so that they take up a room. And it uses components more than once. With a LINAC, each tube is only used once, which is kind of wasteful of resources. Here, obviously it goes around repeatedly. The only problem with them is they only get up to 10 mega electron volts, because after 10 mega electron volts, the particles start to reach relativistic speeds. And we'll come back to this again. But the problem with, once particles get above speeds of about 10 to the 8 meters per second, they start to gain mass instead of gaining speed. And this mucks with our equation, because our whole radius here is built upon the fact that only speed is changing, and therefore our radius changes, and our frequency can match that. But if you've got mass changing, then the synchronization of the frequency of rotation of our particle and the frequency of change of our AC supply is lost. Can we derive the frequency of the AC supply, the frequency at which the particle rotates around the circle? Yes, we can, using the same equation, but a slightly different derivation. So going back to our principle of BQV is equal to the centripetal force. We have a second equation for centripetal force, let's remember, which is mr omega squared. And we know that omega is 2 pi f, so that's where our frequency comes in. So BQV then becomes mr 2 pi f squared. And I'm going to bring this mr underneath. BQV over mr is equal to 2 pi f squared, and I'm leaving that in the brackets for the moment, and you'll see v over r is equal to omega. So we end up with BQ over m, and that omega, that v over r, is going to cancel with one of r's on the right-hand side. BQ over m is equal to 2 pi f, giving us equation for f, BQ over 2 pi m. Now remember, that is the frequency, and that is the 1 over the time period of either the change in the AC supply or the time that the electron spends to do a complete circle. So if you're thinking about the time that it takes to do half a circle, then you need to think about half that time period that's going to match with this. So just be careful with that. Like I've said, this has come up several times as a 6 marker, so if you want to know exactly what you're expected to say, I would suggest you go in, find that 6 marker, and have a look at the mark scheme. It is as I've described, but it will give you a very concise version of what it is that they're expecting you to give in a question like this. One of the questions that comes up a lot: why do we spend so much money producing these particles that go so fast? I mean, these accelerators are extremely expensive, so what is the point of doing this? Why do we want to accelerate particles so much? Well, if we go back to alpha scattering, and I'll put again a link to my video on the nucleus in here, We looked at the structure of the atom by using a technique called alpha scattering, where we fired alpha particles at gold nuclei and watched what happened, how they were scattered by it. And you could do the same thing with electrons in order to probe the structure of the nucleus, because we want to see, okay, we know there's a nucleus there, what's inside the nucleus and then what's inside that. And we can use electrons to do that. Now, if you use a low energy electron, you're going to get what we'd expect. You send the electron in, as in this picture, and it's going to be deflected by the proton. The proton acts like a positive charge cloud. And that tells us something. It will tell us something about the sizes of the protons, etc. But if you want to actually probe the proton itself, then a technique was developed in Stanford again in the 1960s. They led the way in particle explorations. And that is to speed those electrons up and see what comes out. And this is called deep inelastic scattering. Inelastic because in this low energy scenario here, the collision, and that collision should be in inverted commas because they never actually touch, but the collision between the low energy electron and the proton is an elastic collision, so no kinetic energy of the electron is lost. With deep inelastic scattering, we deliberately lose the kinetic energy of the electron. And so you send this high energy electron into the nucleus, you get a collision with the proton, the high energy electron loses a lot of its kinetic energy, and what you get is this fragmentation of the proton and all this shower of particles that come out. And you can look at each of those particles and make some conclusions about them. And of course, if this was the way that we discovered the fundamental particles that the nucleons are made up of. Now, where does the kinetic energy of the electron go? Well, obviously it's going to end up as some of the kinetic energy of those particles. But there's more to it than that. And one of the reasons that we use such high energy electrons, and we've spent so much money accelerating them up, is because we know, again, that E is equal to delta mc squared. And that this is our conversion factor, that 9 times 10 to the 16, the c squared. If we want to make particles, as in just produce particles out of nowhere, apparently out of nowhere, but actually from energy, it's clear that even to produce the smallest amount of mass, we need an enormous amount of energy because our exchange rate here is 9 times 10 to the 16. So to produce any particles, you have to have an awful lot of kinetic energy of the incoming electron. So that's reason number 1. To produce mass, you need lots of energy. And by lots, we mean lots and lots. Reason number 2 is to do with diffraction, because high energy particles can also be used to explore the structure of the nucleus using diffraction studies. But remember, from diffraction, we get the best diffraction patterns produced when the wavelength of the incoming light matches the gaps that we're diffracting that wavelength through. Now, of course, here we're using electrons, and I'm sure you know that particles have their own wavelength, and we use the wavelength of the electrons to study the nucleus by diffraction. And we should also know that the wavelength of any particle obeys de Broglie's equation, which is h over p, or h over mv again. So if we want a small wavelength, so as we decrease this wavelength, we've got to increase the momentum of the particles. In other words, increase their speed. So we've got to get them to super high energies so we can use those electrons as waves to diffract through the particles of the nucleus and see what the nucleus looks like. Okay, let's talk about detectors. During the 20th century, detectors for these particles were a huge deal because we were just starting to explore the internal structure of all atoms. Everybody was getting very excited about what was being produced in these experiments, and so the development of detectors that could tell you what is being produced was a huge deal. So we had these 4 Nobel Prizes being awarded in the 20th century for the different types of detector. Now, you don't need to know the details of any particular type of detector. If they want you to use those details, they'll have to tell you. But they all work on a similar principle, and that is ionization. Charged particles ionize the air around them. And so when you pass them through whatever particular chamber it is, the chambers themselves are only different in that as they pass through and ionize the air, you get condensation of various things on the track of the particle through the chamber because of the ionization. So in a cloud chamber, for example, it is very high humidity in there. There's lots of water vapor. And as the particle passes through and ionizes the air, you get water vapor condensing along the path of that particle, and that's what you see. So here is a classic example of what a particle track looks like. This is a bubble chamber photograph, and we're getting electrons coming in, very energetic electrons coming in from the right-hand side. Let's look at analyzing this track and what we can conclude, because this is the sort of thing you have to be able to do. First of all, if you use Fleming's left-hand rule, remember, if it's an electron coming in, then your middle finger has got to point opposite to the direction the electron is traveling in. We also know that the force on these electrons is going to be towards the center of this circle. That's the direction your thumb is going to point. And what this tells us is that the magnetic field is coming out of the screen. Now, the second conclusion we can make is that the energy of the electron is decreasing, because we can see that the radius of our spiral is becoming less and less. And remember, other things being equal, the radius of the spiral is proportional to the speed of the electron. We're talking about kinetic energy here. So our energy is decreasing because the radius of the spiral is decreasing. And it's losing energy because it's ionizing the material as it goes along. So what would happen if this were a proton? We would get a curl going in the opposite direction. So it would come like this and go around like this, rather than the left-hand side curl. Because, of course, the direction that the particle travels in depends upon the magnetic field and the charge on the particle. So while electrons might have a left-leaning curve in this particular direction of magnetic field, proton would have an opposite-leaning curve. If it were a higher energy electron, what would happen? Well, our line would get straighter. So instead of having this radius of curvature, we would have a much larger radius of curvature. In other words, the line would start to look like it becomes straight. And this is something very important to remember. A straight line here is not the fact that the particle is not curving. It's just that it's moving extremely quickly, and the radius is so large that you're only seeing a tiny section of the circle in which it's traveling. What would happen if it's a neutron rather than an electron or proton? Well, you'd see no track at all, because remember, the track here is due to ionization, and neutrons do not ionize. Okay, so let's look at some classic examples of tracks. The first one are thin, curved paths with a large radius. This means that we have fast charged particles, and if they're in opposite directions, those particles will have opposite charges. So going in one direction, will you have a negatively charged electron, and going the other direction, we'll have a positron, and we'll come back to antimatter later on. So that's number one. Opposite directions means opposite charges, and thin, lightly curved tracks mean high energy particles. A curve like this, where the track gets thicker as it goes along. Obviously, our radius is decreasing, which means that our particle is losing energy, and so it's getting slower. And what tends to happen, of course, is it gets thicker as it loses energy, because as it slows down, it ionizes more particles and loses energy faster as a result. So our circle in which it's traveling gets smaller and smaller and smaller for both reasons. Then we have very thick, very tight tracks. Large, slow particles give tighter, thicker tracks. So remember, our radius again, and I know I keep saying it, the radius depends on the speed of the particle. Remember, of course, that with larger particles, the mass also contributes if you're comparing them, and so we're going to get thicker and smaller radius tracks, but it's a balance between the mass of the particle and its speed, culminating in something that looks like this, which to the uninitiated looks like an extremely mysterious just bunch of squiggles on a page. But once you get used to interpreting particle tracks, you can see what happens. You'd need information, of course, on what the direction of the magnetic field is if you're going to determine the charge on the particle. So we can see that here we've got a particle coming in that is curving towards the right, so we'd need to know what the direction of the magnetic field was in order to determine its charge. But something happens here. And this is where you identify any changes, sudden changes in direction means something has happened. And so we've got an incoming fast particle. We can tell it's fast because the radius of curvature isn't very much, and a decay event happens right there in the center here. And that particle decays into a particle of the same charge as the original because its direction of curvature is the same, and a neutral particle. That neutral particle does not leave a track, so you have this gap that's in there. That neutral particle itself then decays. And of course it's going to decay into two oppositely charged particles because we have to conserve charge. And those two oppositely charged particles then produce their own track. The radius is slightly smaller, which means that our particles are going more slowly, and you'll get little curls as this continues. You'll get your classic turns around these charged particles. We do have to apply our conservation laws here, the same as we do in any collision or explosion in momentum. So this is where things start to connect together. So you can see, and although it's not superbly drawn, these particles go off in those two directions because the momentum has to be conserved. So here we get a particle decaying into two particles, and those go off in opposite directions. The momentum of those two has got to add up to the momentum of the original particle. You could easily get a question on two-dimensional momentum calculations involving particles like this, and I will put a link to my two-dimensional momentum video. And the same thing occurs here. We've got to have a conservation of momentum, and so they go off in opposite directions like this, and in any case, they're oppositely charged. Now, that's conservation of momentum. Conservation of charge. Our initial charged particle comes in, and it breaks into a neutral and a charged particle. That's okay, we've conserved charge because it's clear that this particle here is the same charge as the original particle, so no charge has disappeared. Conservation of charge also happens at the second interaction here because two oppositely charged particles adds up to neutral, and so it is conserved. The other thing that is less easy to calculate for, but you must remember is always conserved, is this idea of mass energy. So although mass may be lost in any of these decays, so the particles may be smaller in mass, they will make up for it by being higher in energy. So the total amount of mass plus the total amount of energy in any of these interactions will add up